All right, give it a start. We'll give it a start. I'll give you like equations and some helpful guide for each question. If you want to ignore my helpful guide, you can do that as well if you want to see, but otherwise you can just use it. At the end, just give me a rough idea how you went. Maybe just multiple choice give you a good idea. So all right, I think it's 2 o'clock to start. Okay, so the multiple choice questions. First question. So they change it to a AC power source. The peak is √2 times VRMS. If they're asking from peak to peak, it's twice the peak or 2 times VRMS, 2√2 times VRMS. Electrostatic force is given by the Coulomb's law, K(Q1, Q2 on R squared). The distance should be in meters, and then the K value, 10 to the power 9. Question 3. Now, some people found it a bit hard, but I think it's just simple maths there. They ask you to find electrostatic or electric field strength from any of the charges. Hey guys, I'm going to send you a paper. I've just started to send that light and matter. The test results. Some people done really extremely well. That's pretty good. Some people not. I will be sending after our revision on Tuesday and Wednesday. Maybe by Friday, I'm sending you a paper. You scan it. I'm expecting you be honest to use 2.5 hours, finish it off, scan it, and send me back. So this is the paper I'm going to use as a guide, how you guys are going and what you guys are going to get at the end. I'm not telling what you guys are going to get, at least that will give you some idea, but I'll mark the paper and give you back. Oh, this is going out of focus. All right. Use a simple maths to find that distance. Your electric field strength is given by KQ on R squared. You have to find R by looking at the simple geometry there. And question 4, guys, just to look at the vector sum. Now you change that question to say that you're looking for the electric field strength. When you say electric force, we need to know whether the charge at the center positive or negative. If it's a negative charge, your answer will be different. So that's why just to get around that, just change it to you're looking for the net electric field strength at the center. Net electric field strength at the center. So what you have to do is look at the vector sum. These two, always treat there's a positive test charge at the center when you're looking at the electric field. Assume that there is a positive test charge. That's what you do when they ask you to find the electric field strength from a positive charge somewhere at a distance r in space. At that point, we are assuming there is a positive 1 Coulomb charge. So based on that, we say the direction would be repelling away. If it is a negative charge, then we say it's attracting. So always be treating this test charge is a positive 1 Coulomb test charge. at the center. Look at the vectors on these two going to be repelling. That's your EA. That's going to repelling EB. Now these two are going to be attracting ED. That's also attracting EC. So based on that, look at the vector sum. I think if you get the horizontal ones, you can see all the components going to cancel out each other. Only the vertical components going to remain there. Conical pendulum, guys. The final equation is going to be very similar to Bank-Rode equation. It's the tension, the component of the tension acting toward the center, mg. You can draw the vector diagram if you want to derive and remind or refresh your memory. That's your net force. That's the angle. You can say tan theta. You don't need to do all that. Tan theta is equal to F net over mg. So basically F net is equal to mg tan theta. At the same time, you can say tan theta is equal to mv squared on r over mg. That's where your tan theta equals v squared rg equation comes in. So the acceleration is g tan theta. That's all what matters for you for that question. Question 6. Conservation of momentum. Conservation of momentum. This is a sticky collision. So therefore, M1 U1 plus M2 U2 equals M1 plus M2 times V. You can combine the masses after collision. Question 7. Elastic collision means the kinetic energy is conserved. Not the total energy is conserved all the time, but kinetic, you're looking for kinetic energy. It's conserved. That means there is no loss in kinetic energy, or total energy before is same as total kinetic energy after. So you need to check it. Let's see what's in. Electromagnetic spectrum. EMS, you stand for electromagnetic spectrum, I guess. I mean, they're not going to ask you about different light, the ways are produced. Not this test paper either. I'm going to send one on Friday. That one, you have to complete it and scan it and send me back. I'll correct it and send you back. I'm going to use whatever the exam that I'm just going to exactly follow the marking scheme and then just mark it. Put in your cheat sheet. Okay, now remember, there are two things when you say frictional forces. In a car, we're talking about this air resistance. In fact, without the friction, car can't move forward. Okay, So the friction on a bank road sometimes help you to have the sideway friction, will help you to go at faster speed. But for year 12, we tend to ignore saying that the road is designed such a manner the car don't need to rely on, or car doesn't need to rely on the sideway friction. So most of the questions will go like that. So if you have the sideway friction, you say if the car want to go then move faster speed than the design speed, which is you can obtain from tan theta equals v squared on rg, then you have to say you have to get the assistance of the sideway friction on that bank road. But they won't ask you to calculate or anything. Could you explain why the car traveled in a vertical bank of the circular path? Yeah, the reason is the car will fall. This is a vertical circular path. The car will fall if you lose the contact force, the normal force. The question is, where does this Fn coming from? Because we always saying it's a normal reaction force. What do you mean by normal reaction force? Means you need to push first. The car need to push the track. Then the track going to push you back. If you can't push the track back, means you're falling. So that means you are in good contact. If you have a greater or equal to 0, that means you have in good contact with the track. That's why it's not falling. So if a person who travel on like a graviton, like in a circular drum, so you can see that you plastered onto the surface, yeah? But you can see your normal force coming that way, mg coming down. And the friction is what holding you, not falling. Forget about the friction and holding. But then you can ask the question, yes, Fn is toward the center. But why the man is not throwing into the center? But a person travel on one of these graviton will tell, faster you go, you feeling like you're getting very, very tight, like you just pushing hard on the surface. You can't even move your arms. That means you need to push the surface first, and then the surface is going to push you back. Because you're pushing the surface so hard, you feel like you really plastered onto the surface. The same thing here. If you go fast enough, the cart will feel like you really push hard onto the surface. The same scenario like a bucket with the water. Yeah? When you're moving around, the mass of the bucket is pushing the bucket first. The mass of the water should push the bucket first, and then as a result, bucket is pushing the water down. So that's force acting on the water. But because that force arriving, first of all, because of the action force, the water not going to fall. What's this? Another question. Do we need to worry about the friction acting towards on the car? Not on a bank road, but you should be able to explain it, not to calculate or anything. Because it's not in a study design with the bank road and sideway friction. On a flat surface, yes, sideway friction comes in, but not with the bank road. Sudesh, what are you asking again? This here. If that makes sense, because the action, could you please explain how a bank curve provides? Oh yeah, for a bank curve, theta. Your center is somewhere here. So the car is going in a vertical, like circular path. Now the car is there. Remember, it's going in a circular path like that. There are two forces acting. The friction is acting, but we just forgetting friction, say that we design the car such a manner the sideway friction can be ignored. So the mg and your normal force. When you combine these two vectors, your Fn and mg, or essentially you have two components. You get a vertical component. So if that is theta, that's become theta. Your vertical component keep the car without flying out from the surface because it's counterbalance the mg. And the horizontal force is the one acting toward the center. Even if you just use that vector diagram, your net force is toward the center. That's what causing. So the component of the normal force acting toward the center of the circular path. So that force is the one centripetal force, which is Fn sine theta. So Fn sine theta becomes your centripetal force. So Fn sine theta is mv squared on r. So the design speed means you have a certain tilt angle. The car can go without relying on sideway friction and also Fn cos theta. That's the vertical forces. So that's the net force, that's the vertical force. We combine them together, you get tan theta equals v squared r, v squared rt. Your design speed is that. The design speed depends on the track radius of the track that you're traveling and the tilt angle. That's why if the guy want to go a faster speed, you can just move upward, go in a bigger radius, or you need to get the assistance from the sideway friction. Had to draw the friction force. No, unless they ask it. Never, they normally don't ask you the friction force. So they ask you to label the forces in VCA, and never seen that question VCA ask you to label the friction. They can ask you to label the net force. So in that case, what do? You label your mg. Because you're designing such a manner, you can ignore the sideway friction. And then your normal force, Fn. And some cases, they can ask you to draw a like dotted line to show the net force. Net force should be flat horizontal line toward the center, not along the incline, flat line, this one, this way, horizontal line toward the center. This is, you do only when they ask you to do that. Otherwise, you stick with that and that, that's it. Okay, I'll get rid of this. If you guys want to derive that equation pretty quickly, easiest way to draw your normal force, mg, that's your net force, which is your mv squared on r, angle theta, then take tan theta, is f net, opposite or adjacent mg, and just replace that, and then you get v squared on rg. That's it. That's for the angle. That's pretty quick. So I've never seen question with the bank road inside it, but you can explain if the driver want to go faster or want to remain on the same radius, then you have to make use of the sideway friction. Yep, design speed is the speed of the car can go in a particular radius without relying on the sideway friction. Okay, question 7. Question 8, impulse. P minus U. Question 9. Feel weightless means just talking about absence of normal force or contact force. But still there is an acceleration toward the center. There's mg acting. There's a net force acting on it. Question 4. So you need to look at the vector sum. So if there's a positive test charge here, that's a positive one, that's a positive, that's a negative, negative. So positive, positive going to repel each other. Let's say A, B, C, D. So that's the electric field strength that way. EB going to be repel each other that way. Even if I take them separately, if you take the horizontal and vertical component, I can say EAX, EAY, and BAX or BX, BY. You can see these going to cancel out each other. Even you do the same thing with the negative charges, they're going to attract that way and that way. You get the same outcome. If you do that, you get the same outcome. That means all the forces acting downward. As a result, your electric field strength will be downward. The horizontal one going to cancel each other. Does that make sense? You need to look at the vectors like positive, positive going to repel that way, positive, positive going to repel that way. And then you think about you splitting that into horizontal and vertical each electric field strength. The horizontal one going to cancel each other because they are identical. The vertical one going to adapt, acting in the same direction. Okay. Question 9, question 10. Now, guys, this is a little bit subject again. Look for the fundamental frequency. The fundamental frequency cannot be 300. If it is 300, at the high order harmonic should be 600. That's 2 times, 3 times 900, and so on. But you have to make your judgment based on the answer they're giving. Looks like the answer showing that your fundamental frequency appears to be 100. Then look for the next 3 adjacent ones. Then look for the other 2 consecutive frequencies. I'm not 100% happy with the question, but just we know that the frequency is going to be NV on 2L. So that means F1, F2 going to be twice that, F3 going to be 3 times that, and so on. Question 11. All right, looks like they're doing an experiment with changing something and looking at the other change. I think best to go for one each option and check what's the best answer. If we change the light intensity, it will change the number of photons. Then that will change the number of electrons emitted, but their stopping voltage remain the same. but you can't really change the photoelectric speed. Is clearly depends on the frequency. And intensity and color, they are two different variables. Intensity is the brightness, color is the frequency. Check the best answer there. Question 12, guys. Now the difference between uncertainty and error. Hey guys, I just posted all the packs that people are requested. I think some of them are maybe on the, I think still with the courier, but others are maybe posted already. If anyone still want to get some practice exams, just let me know, I can send you. Yash, I think your one hasn't received yet, yeah? Yes. Yeah, the same as email ones. Yeah. Which question is that? 9.8, 10, 20. Which question was that? Yeah, that's for the conical pendulum one. Yeah, that's the acceleration. That's correct. There should be an option. 9.8 times 10, 20. Check whether you are in your degrees mode. It has to be in degrees mode. What is tan 20? Tan 20 should be like 0.36 is a tan 20. And then you times by 9.8. Yeah, I'm going to go through unit 3. I'm just starting with fields and then power transmission and then motion. But if you are across like everything, I wouldn't worry about too much. Like then you just do more trial exams or whatever. I'm just trying to help out, especially some therapy, bunch of people like really struggling. Oh yeah, sure. But you send me, send your email. Not email, their postal address. So Ramodu, I think if you are across everything, I wouldn't worry too much. But this is just, there are a bunch of people like need really help. So these are the guys I'm just mostly trying to focus on. But if you want to come on to some sections, that's fine. I'll just like give you like a list of things I'm just going to follow. But again, when I'm just continuing some, like if you guys are saying, okay, yeah, we are pretty good on this section, we don't need to worry too much, then I'll just move on and to a section where, we need to spend more time on that section. That's how I'm just going to run it by looking at your responses. Okay. Can you text your, Sudesh, can you text your postal address so I can send you? Erase the difference between, say, accepted value and measured. Say, example, the accepted value for G, gravitational acceleration, 9.8, just argument's sake, at a particular place. Your measured value, say 10.2. So the error in your measurement, you can say that 0.4. Uncertainty is the range of values that you can have in your measurement. Based on instrument accuracy, and systematic errors. Random errors, you try to minimize it by having more trials. Still, you can have some systematic, random errors, etc. Example, your answer say that your G is 10.2 plus or minus 0.3, means the range could be 9.9 to 10.5. That's your range. All right, that's question 12. Your uncertainty is the range. Now, this is again a bit of a tricky one. Again, can be subjective. I'll tell you the meaning of refuted means proven to be incorrect, or wrong, or false. So you came up with the hypothesis. Like, remember, we haven't gone through refractive index questions because that's constant Snell's law. Question 10, why not? Because these are both then fixed. With both then fixed, it's going to be multiple. Guitar string has both then fixed. It's going to be 100, 200, 300, 400, and so on. If the fundament is 100, all the multiple of that would be the high order harmonics. Because remember, n equals 1, 2, 3. Any n value, you can have it. It's only the one and free ones, only odd harmonics are possible. If both ends are fixed, then you can have 100, 200, 300, 400, and so on. That makes sense? Yeah, but we're looking at the 3 consecutive ones. That's why the question was not great, but we're looking for 3 consecutive ones. So based on the answers, you have to pick that's 100 as the fundamental, and what's the next 2, including 300. Okay, question 14. Yep, so they mixed up, I think, whatever, question 13, in their assumption, they mixed up the mass density versus optical density. Mass density will decide whether oil is going to float or not. That's not necessarily true when you're considering the optical density. That's the transmission of light. How much the speed of light going to affect. That's the refractive index essentially telling you. So that's what we call optical density. So they based on their assumption was, or hypothesis was basically, it's wrong because they are based on the mass density of the object or product. Question 14. Now, longer the wavelength, greater the diffraction. In your electromagnetic spectrum, so that's the visible. So that's ultraviolet, X-rays, gamma rays comes under this region. Their wavelength is much shorter than infrared, microwaves, radio waves. Their wavelengths are much longer. So if I draw that wavelength here, representation is getting smaller and smaller. Something like that. So lambda increases that way. Let's maybe get rid of some of the questions from here. Question 1, 2. Question 15. You look at the standing wave. The whole length is 1.8 meters. So you can see the D is lambda on 2. Last bit is lambda on 4. So 3 lambda on 2 sections. And then you find the D. Question 16. Yeah, 16 is Doppler, so forget about that. 17. That's experiment 1, experiment 2. So lower photocurrent means lower intensity. Greater stopping voltage means that's the stopping voltage. Higher frequency or smaller lambda. Question 18, as I mentioned, treat these patterns have the same spacing. Question 19, so you need to think about in terms of de Broglie's explanation, the forming of standing waves. Yep, didn't work. Question 20, you can ignore that Heisenberg. Uncertain principle. No, Doppler effect they taken off this year. So question 16 just ignore. Yeah, question 16. Doppler effect, Heisenberg uncertainty, they taken off this year's study design. No, so they definitely taken off Doppler effect. Check my. If you do a search on the study design this year. I don't know whether you can see that camera. Yeah, maybe you can't. Yeah, they're taken off Doppler. Maybe not. Yeah. Anyway, so they cross it off, explain the qualitatively the Doppler effect. There was no calculation for Doppler effect even before, but they just say explain qualitatively the Doppler effect. Question like that, they taken off from the study design. Okay, I'll put the answers, guys. Question 15. Yeah, so they ask you to find that D, distance D. Distance D, you can see is the half wavelength. So this is like the seventh harmonic. Remember fundamental? Third harmonic, because you can't produce even harmonic with one in free. And that's the fifth harmonic. And that one is the seventh harmonic. So if you start counting from node to node, that distance is half a wavelength. So 1, 2, 3. 3 half wavelengths here. Plus the last bit is a quarter. This is a quarter. This one is a quarter of a wavelength. So if I simplify that, that's going to be 7 lambda on 4. So just solve for lambda. 4 times 1.8 divided by 7. What's that going to give you? 4 times 1.8 divided by 7. That will give you 1.028 meters. Therefore, D is going to be half that. Half that you divide by 2. You get 0.51 meters. That's the answer for question 15. That makes sense?
Yep, thanks.
Okay, so I'll put the answers, guys. Is everyone finish the question, or still some people are doing? Maybe? You can just tell me a quick rundown how you guys going. I'll get rid of these questions. The answers. Just be Yeah, this is a bit difficult, like which one to select. Yeah, so to put a transformer, we have to place a transformer. Yes, that definitely. In terms of circuits, yeah, I think with the transformer, not the complex circuits, but if they say, okay, now we're going to introduce a transformer, draw modify the diagram or whatever with the transformer on. So they can ask you that kind of question. That's quite possible. Yeah, that's good, Rahan. Akshat, yeah, that's good. Do you guys want me to go through the questions that you guys made wrong? Okay, it's okay. Okay, all right. Yeah, that's good. That's good. But is that without my help or just with some guidance from the board? Question 3, yeah, of course. Question 3. Is that the one with the? I'll get rid of this here. Question 3 is the one with the charges. The identical charges, negative, negative. So this just simply asks you to find electric field strength at the center from one of the charges. So the part is like you need to find that distance. So each side length are A, so that half the length you need to get that half the length at A on 2. A on 2. That's the distance. So if I use Pythagoras, I get R squared is equal to plus. If I expand it, I get 2A squared on 4. I get A squared on 2. Then you sub it into this equation, KQ on R squared. So KQ on A squared, your 2 will come to the top. So that's what you can answer it. Okay, Pratham, yeah, it's good. Okay. Yeah, it's worth, guys, just putting the time to effort to read the questions always useful. Okay. Right, we'll just move on to the short answers, guys. Yeah. Without it's great. Without help would be great. Yeah. Maybe with the time, I'll just minimize, just give maybe like just I don't know, even the equation I should not give. Maybe I'll have a look with the time, little by little, just reduce the amount of help. Okay. Go ahead. The short answers. The people are quiet, not telling me anything. Hey guys, just open up a bit. Yep, okay, that's good. Where is Dinura Ashuka? Ashuka is done. Nihindu. Hey Nihindu, I posted your pack as well. I'm not sure. It looks like it hasn't delivered yet. Probably Monday. For the question, how many minutes do we spend on each question? Like many minutes? Yeah, generally the guide is you have like, because 2.5 hours, I would say 1 minute, 1 mark. So you have 2.5 hours, that is 2.5 times 3,600. So you have 9,000 seconds. You have 130 marks worth of questions. So divide by 60. You have like 69 seconds for each question. So that means just keep it like 60. So just keep it 1 minute, 1 mark. So for first 20, yeah, so it's a choice. It's a personal choice. Like if you guys feel like you're spending too much time on your show, the multi-choice, don't forget that there's 110 marks in the short answer. So when you're doing revising, it's just good multi-choice because it covers the whole section. But in trial exam, like you're doing like just timing out and say, maybe go, not a bad idea, go for short answer and then come back. You can spend, save some time. Some kids are saying that already, that when they're doing trial exam, they're finishing off like with half an hour in advance. Even trial exams, that's could be scary because that means you're doing lots of careless mistakes, or maybe the guy may be extremely good. The VCE exam, you can finish a bit early. Definitely everyone will have at least 10 minutes or 15 minutes advance at finishing off exam a bit early, provided that you prepare well. Okay. I think VCE multi-choice question, I'm pretty sure you can finish it off maximum 25 minutes. Then you had to catch up the time from the other sections. Main thing, people are aiming high. You need to tackle that 5 to 7% hard questions. Remember, it's just a ranking again, so you need to try those ones. Spring question, plus maybe, I don't know, transformers or maybe wave questions will be there to differentiate the kids. So. Right hand slap rule. Remember positive charge. You keep the thumb in the direction of the positive charge. Do not put into the opposite. That's for the electron. Thumb should be pointing in the direction of positive charge. That's the conventional current. Okay, do that. Thumb is going that way, the fingers are going that way, and the force is acting up like that. Part B. The charge of a proton and electron is the same. You should get a value 1.6 times 10 to the power negative 14 newtons. Now part C, this is the question you asked from. This is a combination of electric field and the magnetic field. So if I want to send my particles straight without any deviation, I need to make this magnetic force to be zero or net force to be zero. Only way you can achieve that is applying the electric field so that the electrostatic force or electric force is acting opposite and equal. Then your F net becomes zero. Then particle can go straight line. So how do you do that? I know that Because of the magnetic field, the force is up already because the particle entering perpendicular to the magnetic field. The constant force perpendicular to the direction of the motion is always acting. If I want to make its electric force to be down, I need to have a negative plate here. That's where the positive proton going to attract. And positive plate there. Remember, do not use right-hand slap rule for electric force. Right-hand slap rule acting only for the magnetic forces. You need to have three variables. Okay, the speed, force, and the magnetic field. But there's two, electric field and the force. Either that force is parallel to the electric field. If it is a positive charge, it would be parallel. If it is a negative charge, it's anti-parallel. It's going other way. So electric field is always from positive to negative. That's what they trying to draw. Positive to negative. Why negative? It's a positive charge. Proton should attract. Net force has to be zero. Yeah, constant velocity, part D. Should be down. They say the coil is rotating clockwise. So you have to use the right-hand slap rule. The magnetic field is north to south, so magnetic field is like that way. and the force should be pointing up, and palm should be pointing up, and then you can see thumb is pointing, I don't know how to draw, thumb is pointing like that way. The thumb should be pointing in that direction. So if I connect the battery, the current should be leaving here. If it is leaving, that should be positive. Use the slap rule. People having trouble slap rule. Work it out the direction of the current flow. Magnetic field is north to south. Would the diffraction be bigger if the wavelength and width are approximately the same size, or the wavelength is much bigger? So there's a limit that generally we're saying, okay, the wavelength should be bigger, the wavelength gets the better the diffraction. But if they're comparable, the size-wise they're comparable, they can get a significant diffraction. And when you come to the other thing that you have to be careful is when you're looking at the diffraction through crystals, because of the interaction between like electrons, protons, neutrons. In that case, we're not looking at a ratio of 1 or close to 1. So we then, in that case, we're looking for the order of magnitude. If the lambda is say 10 to the power negative 10, W is also 10 to the power negative 10, regardless of you might be getting your ratio is 0.5 or something, 0.4. Still we say there's significant diffraction. Okay, so order of magnitude. So generally we can consider as lambda is bigger better, but the best diffraction would be when they are comparable in size. Remember that point. So when you're talking about diffraction through crystals from particles, always look for the order of magnitude rather than looking at the ratio equal to 1. So NEEP always saying even the ratio of 0.1, you produce good diffraction. But I would stick with the order of magnitude, checking the order of magnitude. Okay, so who is correct? not acting on the same line means like see this going that way, that one's going that way. If they're acting on the same line, then the torque will be zero. Say for example, this scenario, the torque will be zero. Here, torque is maximum. If it is horizontal, torque is maximum. If it is vertical, torque is zero. Question 3. You need to ignore that little opening there. Just get the area. How about question 1? You guys done with question 1? Can remove it or? Okay, I'm going to wipe question 1. If you haven't finished, take a screenshot, guys. Quickly. Question 1. Anyone have trouble with question 1? Question 2? When question 3? Or maybe I can squeeze question part C. 3C here. EMF. I think it says somewhere in the question, say n equals 10. Average EMF 4.5 times 10 to the power negative 3 volts. That's 3C. I'm going to get rid of question 1, guys. Question 4 is the Lenz's law question. They say the coil is rotating clockwise. Initial magnetic flux is 0. It's increasing. Increases in terms of the field, we can say it's increasing to the left. If I rotate like 90 degrees, this is what you're getting. I will draw these black lines, indicate this is the external magnetic field. Provided by the magnets. That's increasing. In terms of the strength is increasing to the left. Now as a result, to oppose that, the induced magnetic field is the red line. Red arrows rather. Induced magnetic field. To the right. And also it's increasing. This is just to oppose it. Then right hand grip move. Coordinate length is low. The magnetic field produced by the induced current. Magnetic field produced by induced current. Increases to the right. To oppose change. Now you have to use the right hand grip rule. The thumb should be pointing in the direction of the induced magnetic field. And curl your fingers around. I'm just using like a solenoid rule. Something like that. Like doing that. So the current flow going to be like that. Then trace your path through. Be careful, sometimes they can ask you the current flow through the coil or through the ammeter. In this case, they are asking through the ammeter, X to Y. From X to Y. 3C, okay, 3C. Oh yeah, sure. 3C. So what you have to do, because your magnetic flux is that, yeah? 3C. They say at the beginning of stem of the question, number of turns is 10. You can forget about negative sign, number of turns is 10. And the flux is that, initial flux is 0. So initial flux is, the final flux is 0, initial flux is that, 10 to the power negative 4. You can keep your negative signs, as can cancel. And the time it takes to come out from here to here, that's where the variation happening in 2 seconds. So you can see 9 divided by 2 is 4.5. 4.5 times 10 to the power negative 4. And then you times by 10, it will give you 4.5 times negative 3. So that will give you 4.5 negative 3 volts. Number of turns 10. Final flux is 0. Initial flux is that. Time is 2 seconds. 2 seconds. See, this is where the flux is changing. Okay. Why? Because they're rotating clockwise. Pretty sure it's X to Y. Kathum, can you check it again? Because you're rotating horizontal flat to vertical. The flux is your magnetic field is like in north and south. The south pole is here. North pole is here, south pole is there. The magnetic field produced by the magnets is to the left. That's north, that's south. So therefore the flux is increasing, or strength of the magnetic field is increasing to the left. So the induced field should be to the right. If the induced field to the right, my thumb should be pointing that way. And I curl my hand around like that. I'm using the solenoid rule. I'm using my thumb for the magnetic field. It's easier to curl around. Okay. Okay, guys, I'm going to get rid of question number 2. Is that okay? Question number 2. All right, so the scenario is you have a solenoid where you're supplying the current to it. Because of that, there will be a change in flux in the coil next to it, rectangular coil next to it. Something like that. So now what they're connecting is the AC power supply. The direction the current going to be changing continuously. The flux going to change the direction continuously. At the beginning, maybe it goes like that, but that's not going to stay forever. It's going to continuously change. The flux through the rectangular coil would be changing. So the induced current happening in the coil. Induced current happening in the coil, the frequency is 50 Hertz. The period is going to be 1 on 50, 1 on F. That's 20 milliseconds. They say not to worry about the magnitude of the flux, the maximum value. So at t equals 0, they say no current. Therefore, flux through the coil is 0. Is the rectangular coil we're talking about, not here. We're talking about the rectangular coil. That's the one going to have the induced EMF later on. Ask it to draw for 40 milliseconds. So maybe that's 20. That's 40. That's for the full period, okay? Full cycle. That's 10, 5, 15, 30, 25, 40, 35. So starting from 0, that's a flux. They say not to worry about the value for Y, but be consistent, the same amount of positive and negative. Okay. That's your flux graph. Now they talk about the EMF. They're giving EMF at a given instant. You half the frequency, the frequency is half. EMF will half. Not only that, the period will double. That's the original one. They're giving that for 40 milliseconds, 2 cycles. You need to draw half that, now double the period. You can fit only 1 cycle. Or there are more than, okay, just 40. You can fit only 1 cycle, half the height. Something like that. Question 6. Question 5. There is no working as such. Only working is just to find the period. Okay. Okay, I'll get rid of this question 3. So now question 6. It's a quite simple question, question 6. Now treat, this is the ampere, this is the load that you are trying to drop your voltage. That's where you need to supply. But your voltmeter registers here 7.5. The current here is 1.5. You can see there's a drop of that, take away that. Unit resistance is 12 take away 7.5. You're dropping 4.5 volts because there are some resistance here and here. So the total resistance in the line, use the Ohm's law. It's using Ohm's law, and then therefore resistance in each line. Okay, part B. I'm going to get rid of question number 4 here. Guys, okay if I remove question number 4? Now you have a transformer. You're stepping up. You're stepping up the voltage means you're stepping down the current. Don't forget that your transmission line is still the same. Our total here is 3 ohms. And then you're introducing a step down. Stepping up by factor of 10, stepping down by factor of 10. This is 12 volts. If we look at the secondary voltage, 120. And part C, the current in the transmission line. N1 on N2. I hope all those. Zero 068. They're asking how much voltage received by the load. At the step down. VP going to be 120, take away that voltage. Therefore, the voltage at the load divide by 10. Isolate that 1 kilogram for this one. These are very easy questions here. 51. 4.9. Mass times acceleration. Part B, you can do a couple of ways, but easier to isolate two together. Trying to find FT2. It's 1 kilogram, 2 kilogram. .7 times. If two spaceships travel towards each other, they both measure the time until they meet. Who measures the proper time? What time they're measuring? That's the question. Are they measuring their own travel time, or they're trying to measure each individual one's travel? That's the question. Their own time. They both measure proper time. They both measure proper time because they are measuring their own event. That means you're trying to measure, like say, spaceship, the guys observing spaceship A, trying to estimate the time for the trip of spaceship B. You're trying to measure someone else's frame. Then you would measure the dilated time. And the other guy trying to measure your time, then they both measure individually dilated time. If you are measuring your own travel time, that you always measure proper time, because your event happening in your own frame of reference. Yeah. Yeah, remember. No, remember, like if the two people are measuring the same event, okay, same event, and one person measuring the time, same event, like one measuring the time, if that time is happening in the first person's frame of reference, he measured the proper time. Now the same event measured by another guy in a different frame of reference, remember, same event, then he will measure the dilated time. The length is the same. If we try to measure the length of an object where the object is at rest on my frame of reference, I would measure the proper length. If the other guy is trying to measure the length of the object from his own frame of reference, then he will measure the contractile length. No, because it depends on what event. If they're observing the same event by the two frame of reference, that's where the time dilation and length contraction happens. Question 8, the projectile one. I'm going to get rid of this guy. Is that okay? Question number 5. Hey guys, in terms of revision, like when you started, like we started doing these things like weeks ago, do you guys think that you guys getting any benefit out of it, or you guys feeling still a lot to revise? What's your personal feeling? Is that helpful, like the way that we're doing it? Just give some feedback, guys. What do you think? Is that things coming back to your memory? Yeah. Okay. All right, that's good. Okay, that's good. That's good. Question 8, so simple projectile. Now, when you talk about projectile, always think about these two independent motions. It's a combination of these two independent motions, what you see in the path. You're projecting at 7 meters per second. You need to split this into two components. So remember your horizontal and vertical components. Seven cos 60. Your vertical is 7 sine 60. Now they ask you to find the time that takes that basketball or whatever to reach that hoop. So that time would be same as, remember the motion while it's moving up and down is traveling laterally sideways as well. It's like that. We're going to make use of this sideways motion. There are no forces, horizontally no forces. So the acceleration is 0. Therefore, I'm going to make use of that. So now keep in mind, this is not a derived formula. This is just saying my distance is equal to horizontal speed times time. Just speed equal distance over time. Simple as that. So make use of that to find the time. The answer would be 0.8 seconds. Because we're making use of that range to work out your value. Okay, that's going to be 3.5 basically. Cos 60 is half. And part B, we're trying to find the height, this height. So it's a vertical quantity. We don't want the speed here. So the only equation that you can avoid the final speed is that ut. But remember, it's a vertical. So taking up as positive, your h should be something like that. That's your projectile. Question 9. Okay, good. All right, question 6. I can remove question 6 if you guys done or part of the question 6 at least. Then I can introduce question 9 there. Do you think I can remove part of question 6, guys? What do you think? Yes. I'm going to remove the first part of the question 6. It's quite simple. Question 8. To find the height, the problem is you don't know the speed at the top here. At the dish, you don't know. You can use it, but you don't know the speed of the. So you need to find that one separately. So you can say half times m times 7 squared is equal to mgh plus half mv squared at that point. We don't know v. So unless you can find the vertical and horizontal stays constant, which is 3.5, that's extra step there. Is that what you thinking, Rahul? Because you need to find your speed. You need to find the speed near the dish. Nothing wrong, as long as you know the speed there. No, because you're comparing the initial energy, which is half times mass times 7 squared, to the energy, total energy at the top near the dish. So that would be you have a kinetic energy plus the gravitational potential energy. Okay. Yep, that's correct. I think 3.7 or something. 9b 3.7, as I remember. I think 3.8 maybe. Yeah, close, very close. Question 9. So start from a certain height. So they're asking what's the minimum speed. We know that minimum speed is given by root rg. And let's just refresh how we get that. At the top, remember always net force is a centripetal force. Centripetal force is a net force. So mg mv squared on r. This is at the top. At minimum speed, you momentarily lose contact force. Your Fn becomes 0. So that simplified root Rg, which give a value of 1.21 meters per second. Convert centimeters to meters. Part B, you can use conservation of energy. Total mechanical energy at the top. At B, you equate the total mechanical energy at A. It's conservation of energy. So mg times your diameter, which is 30 centimeters, plus half times mass times 0.121 squared equal to mg times height. You can cancel m, so you should get like 0.37 meters. I got 0.37, just check whether it's a 0.37 or 0.38. Okay. Okay, 6b, I'll get rid of this. Question 10. Now, remember guys, question, can we apply Hooke's law? Yes, you can apply Hooke's law to any point, but you cannot equate the spring force to mg unless the object is completely at rest or the acceleration of the object is 0. If not, you have to use conservation of energy. Now, significant figures, they're not penalizing for physics in significant figures. There will be a couple of questions, one or two questions. They will ask you to give the answer to 2 significant figures or 3 significant figures. Unlike chemistry, they don't penalize it. Don't leave exact value. Maybe just keep it rounded up at like 2 decimal places or something. Okay. Yeah, they will definitely specify which question. Just have a look last year before. They will say this particular question give you an answer to 2 significant figures or 3 significant figures. They're not using like in chemistry. Chemistry, like there's a yeah, that's a teacher's discretion. Yeah, sometimes they can take marks off for significant figures. But VCA exam, this is the first thing when you go for the assessor's training day. That's the first thing that they're doing, saying is we're not penalizing, but for that particular question, they're asking for, you have to do it. Otherwise, yeah. I mean, don't keep it like 5 decimal places or something. Keep it sensible. Like I just rule of thumb, like keep the answers at 2 decimal places. Yeah, unless they ask you to do. But remember the progressive rounding up, they're very critical on that. If you keep on rounding up and finally you say, for example, you calculate a value, you need that value for to sub into a different answer. The guide is, if you have the exact number, use that exact number, or at least 4 decimal places of that number. Okay, progressive rounding up, they will take marks off. Drawing the line of basic, do you extrapolate? No, the extrapolation is you have to be very careful unless you really know that it's going through the origin or something, or you know how the shape is. Otherwise, you just stick with the data points that you have. But if you know, if it is definitely following y equals mx or y equals mx plus c, like say for an example, photoelectric questions, we know that. But then you can do it. But otherwise, if you have a set of experimental data, you stick with that, the data that you have. All right. So question 10. So this is a situation where you attach a spring. So I was trying to show that it's not a great demonstration, but there is another spring. If you connect the mass to here, so I'm holding it. Once I release it, you can see it's going to the maximum, and then after a few oscillations, if I can hold it, then it's a rest position. Then you can say my spring force is equal to mg. Your k delta x equal to mg. Now I can say, but you cannot say that when it's at the maximum extension. Here you can't say that because your spring force is quite big than mg. Even the object is momentally at rest, is about to bounce upward. Okay, so you have to use a conservation of energy. They say momentarily at rest means that's basically maximum extension. If net equals not zero, so your spring force is big here. That's K delta X. Because your mg doesn't change, but the spring force continuously changing with the extension. So if I just use that as my GP 0, and that's the topmost point, use conservation of energy. Do not equate the two forces at this point. You cannot, although it's momentarily zero, that doesn't mean the two forces are equal and opposite. No, the spring force is bigger. It's about to accelerate upward, that move back upward. Conservation of energy, so you can say mg delta x, that's the GP at the top. That's all you have. The spring potential energy at the bottom. At the top bottom, you have only the spring potential energy. Delta x can't be zero. So therefore, I'm trying to find the K, 2 mg on delta x. That will give you 40 newtons per meter as required. Okay, the next part of the question, you can say that acceleration is maximum soon after you release it, which is 9.8. So they give it 3 marks. Maybe just derive an expression for acceleration and then show that acceleration become maximum when delta x equal to 0. So that's mg. That's your spring force. Okay, delta x is acting opposite to the extension. Your net force, if I take down as positive, mg minus k delta x. Remember, your mg doesn't change. I want to get an expression for acceleration, so divide both sides by m. Or using m. Then you can say that the acceleration become maximum. You can plot a graph as well. Delta x equals 0. So that means the acceleration becomes 9.8. So now you release the block. If you really want to plot a graph, if that's the acceleration, that's your delta x. The graph looks like that. This is where the maximum speed occurs. Acceleration is 0. Because until that point, object is speeding up. Maximum speed occurs when A equals 0. That's soon after the release. You don't need the graph for the question, but saying that. Question 11. Remember to convert kilometers to meters, the mass of the Earth. 24. Your R value. Part B, you can just say that acceleration is, you can write it like this, 4 pi squared r on t squared, and find the t. When you sub the values, you can put that a here, or g or whatever. Should get, in terms of seconds, you should get that. For 12 hours. Question 12. You can argue that way as well. You can argue because then you have to say that so that's going to be twice the extension at the when it's at rest position, yeah, twice the extension. So that means this value should be equal to 19.6. And based on that, you had to find delta x. You have a point there, but the question, what's the question? How the question asking? Calculate the greatest acceleration of the mass X when you arrive the results. Can you show that if you put delta x on as, if you can show that if you delta x equal to 0.49, what do you get? K is 40, that's 2 kilogram, 1 kilogram mass. If you get 19.6, it should work. So 40 times 0.49. Yeah, then you get that as well. So that you can say that as well. You can say at that point was as well as here. So that's again 9.8. The question they're asking, determine the value. So basically they're asking what's the greatest acceleration. Either way, you get 9.8. Yeah, you can mention that you can get the greatest acceleration soon after release and also when it's at momentarily at rest. I think it's a good point. Good point. Momentarily at rest. Either case, you get 9.8. Question 11. Question 12. They ask you to find the, remember, relativistic mass. Is the gamma times rest mass. So gamma, you can find it using V squared on C squared. You should get like 7.09. Then the relativistic mass going to be, they're giving the mass of the muon in terms of the mass of a proton, a mass of electron. When you do that, you should get 167 times the rest mass of an electron. the B part B. So the chamber is in a scientist frame of reference. So the scientist will measure proper length. So that means 1,000 meters, that's a proper length. So therefore, electrons will measure contracted. (141 meters). You can ignore question 13. Question 13 is can we quickly finish it off the graph, guys? We haven't done any graphs. Is that okay? Or maybe I'll just remove that. So the graphing, the students are measuring the fundamental frequency by changing the length of the string. Experiment is changing length and measure F naught or fundamental frequency. Remember, for both end fixed. So the nth frequency is given by that. So n equals 1, that's the fundamental frequency. Therefore, your F naught or F or whatever is going to be, or maybe say F1, be on 2L. We want to rearrange this into y equals mx type. So maybe just say F. Because the speed depends on the tension, the temperature, so we're not changing any of that, but simply changing the length. And that's 1 on L. So this part becomes your y. That's become your x. This is your gradient. Now, when you're plotting the graph, guys, you don't need to start from 0 because you need to spread your data as much as possible. That's your x-axis. Because if you look at the range of 1L is per meter, you can start like 1.5 up to maximum of 3.13. So you can go 2, 2.5, 3, maybe 3.5 there. Your frequency you can vary 370 to 655. You can start with 300, maybe 600 somewhere there, 400, so 400, 500, 600. Plot the graph. First point is 1.75 times 370, 1.75 somewhere in the middle. 370, maybe there. Use a pencil. For the graphs, I would recommend use a pencil. If you make a mistake, you can wipe it out. 1.92, 400, 2.13. That's about 450 somewhere. 2.38, maybe 2.25, 2.38 somewhere there. That's 500. 2.7, that's in the middle somewhere. 570. 3.13. 655, 600, 655 maybe somewhere there. And then the line of best fit. Line of best fit, you even out your data point. If there's a spread, you had even out. Just one single line. Just use a ruler. Nice straight, one single line. No, don't break it. Just one single line. Use a ruler. One single line. Don't do in 2 steps. Then you can see your gradient is changing. And you have to find your gradient to find the speed. Do not pick a point from the table. Don't pick a single point and calculate the speed. You lose marks. You have to find the gradient. You have to find the gradient. Pick nice 2 points from the graph. If the points are from the table sitting on the graph, that's fine. But otherwise, pick 2 points. The gradient. Your gradient should be like 206, something like that. Roughly plus or minus about 2%. And your velocity, because this gradient is beyond 2. Therefore, your velocity should be about 413 meters per second. 413 meters per second. If you guys don't understand why I'm doubling, because of this gradient. Gradient is half the wavelength, half the speed of the wave. Nice, straight line of best fit. Can you to simplify? Why can't you simplify? I didn't get it, Akshat. What's the question? Why can't you simplify? G equals 4.49. Just to show what delta x you mean. No. Akshat, can you just elaborate what you're trying to say? I really didn't get. This is for the spring question, I guess. No, G over 49. Okay. All right. So there are a couple of more questions, guys. One is a photoelectric, and again the matter wave kind of question. I think they're not hard questions, but last question, guys, don't omit. The last question is where you're talking about you sending through one electron at a time through double slits. So you had to mention about initial observation on the screen. When you send one electron at a time through these double slits, and they're giving the slits vertically. Yeah. So what you see on the screen, a bit of spread of bright spots. You can't really see any pattern there. So you might argue like, okay, it's showing the particle behavior. Initial observation is going to be random bright spots. The randomness has some meaning because electrons coming through the slits and they deviated into certain direction by wave behavior, but we can't say anything about these ones until you see a clear pattern forming after a while. that you can see that there is a certain probability where the electron need to be landing on the screen. But talk about interference. Don't talk about too much on diffraction. Yes, they diffract through the slits, but forming an interference pattern. Interference pattern is showing the wave behavior. Okay, that's what for the weaker one. So talk about at the beginning, what you see a random distribution of bright spots, which showing the wave particle behavior. Over the time, a clear pattern is emerging, which is clearly showing a interference pattern on the screen, which is showing a wave behavior. All right. Any question, guys? Otherwise, I need to stop there. But please finish it off, the remaining 3 questions. 17, 18, 19. 17, 18, 19, yeah. The question 18 is quite simple. If you look at it, the gray sections are the construct interference points because we're using the center as our guide. The central dark dot they're showing is the central band, which is a bright band. So all the gray lines should be the construct interference points. Okay. So whoever want to come in, join in on Tuesday 5 to 9, and then Tuesday 5 to 9, Wednesday morning 9 to 1. I'll just give you a little bit more information. If I can finish it off my materials before that, maybe I'll send you as well. Okay, guys. I'll let you guys go. If you guys can sit there and then finish it off, the questions, remaining questions, that would be really nice. If someone has already finished, that would be really great. And quiet people, please be vocal at least now. At this stage, you have 6.5 weeks to go. 6 and a bit weeks to go, so not many weeks left. Trying to maximize as possible. This is a very awkward year, but you know, hopefully we all survive. Okay, anyone still need practice exams or anything, just let me know, send you a post letters. What mark you should aim for? Okay, now I would say like 40, just rough row 40 you need. It varies maybe at like 88%, say 45, 93, 94%, close to aim up 95. I think you guys can do it. Main thing that you need to tackle that hard questions. Other questions are very repetitive. Yes, when you get the paper, you feel like, oh, that's too easy, but be careful with that few questions. Yeah. SAC average, depends on the school. Now, generally, the bad news for your school last year was it was scaled down. That's why I always like harder SACs. That's always helpful. But if you do really well in the exam, yeah, I guess so, yeah. Yeah. I think the SAC average, I think they're scaling up, but still not great. I don't know, because I still not understanding the way that they're running the SACs. Yeah. So they're just doing 3 together and then doing here and there. Hard to see a 50 coming up. In last year there was a 50. I think there was a 50 last year. So I remember 150 maybe. But it's very difficult to see too many 50s coming up from your school. That's pretty sad. Like for your school, normally you should expect more. But yeah. But let's see. Keep our faith. Yeah. Work hard. Yeah. If your SAC marks are like at least high A or something, if you can't get A plus, at least high A, that will help from schools like you guys. So SAC marks around, depends on the school again, as I said, at least 86, 87% and above would help. But if you don't screw up the exam, that's the main thing. Bottom line, don't screw up the exam too well. Okay, guys, I think to be honest, like pretty much most of you guys can get above 40 if you're serious, but let's see. Okay. Okay, I'll let you guys go. Have a good evening.
Thank you, sir. You too.
Goodbye.
Thanks.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Goodbye.